In this video, we will talk about descriptive statistics. Descriptive statistics are values that are calculated to summarize a set of data. The two types of descriptive statistics that we'll talk about in this video are measures of central tendency and measures of dispersion. Measures of central tendency are used to calculate the most usual or the most typical value in a set of data. Measures of dispersion are used to calculate the amount of dispersion or the amount of spread in a set of data. The three measures of central tendency that we'll talk about are the mean, median, and mode. The four types of measures of dispersion that we'll talk about are the range, mean absolute deviation, variance, and standard deviation. This is a made-up set of data from 5 college students. We have age, which is a quantitative variable. We have number of units, which is a quantitative variable. We have number of children, which is a quantitative variable. We have grade level, which is an ordinal variable, and college major, which is a nominal variable. You can only calculate a mean with a set of quantitative data. So since age is a quantitative variable, these data values under here are a set of quantitative data, which means that we can calculate the mean of these data values. How do you calculate the mean of these data values? We can add up the numbers and divide the total by the number of numbers. We add up all 5 data values and we divide the total by 5, since we have 5 numbers in this column of data. Let's find out what the total equals. The total is 130, and we divide by 5 to get 26. The mean age in this data set is 26. I said that you can only calculate a mean with a set of quantitative data. Number of units is a quantitative variable, which means that the 5 numbers under here are a set of quantitative data. Since these 5 numbers are a set of quantitative data, you can calculate the mean of these 5 numbers. To calculate the mean, you have to add up the 5 numbers and divide the total by 5. We divide by 5 since we have 5 numbers. Let's find out what the total equals. The total is 65. And 65 divided by 5 is 13. Sorry, I think I didn't show you all of the work here. We added up all 5 numbers. We got our total of 130. And then we divided 130 by 5. And we got our mean of 26. So the mean age was 26. I already wrote that down over here. The mean number of units is 13. What about number of children? Number of children is a quantitative variable, which means that we can calculate the mean of these 5 data values down here. If we add the numbers on top, we get 5, because 2 plus 2 plus 1 is 5. We don't have to include the zeros, because they don't change the answer. If we divide 5 by 5, we get 1. The mean number of children in this data set is 1. We can only calculate the mean for the columns that are quantitative variables. So age is quantitative, so we can calculate a mean. Number of units is quantitative, so we can calculate a mean. Number of children is quantitative, so we can calculate a mean. We can't calculate a mean grade level because grade level is an ordinal variable. We can't add up these 5 answers and divide the total by 5. We also can't calculate the mean college major because these 5 answers are nominal. So we can't add up the 5 answers and divide the total by 5. So overall, we can calculate the mean for all of the columns that are quantitative, which are these 3 over here, and we can't calculate the mean for the columns that are qualitative over here. Qualitative means either nominal or ordinal. So we won't calculate the means of these 2 columns. We need to remember that the 5 right here is the number of numbers. So since there was 5 numbers in this column, we divided the total of the numbers by 5. Since there was 5 numbers in this column, we divided the total by 5. And since there was 5 numbers in this column, we divided the total of those numbers by 5. That's how we got the mean of all 3 columns of data. Now, I said that the mean can only be calculated with a set of quantitative data. Since age is a quantitative variable, these 5 numbers are a set of quantitative data. Since number of units is a quantitative variable, these 5 numbers are a set of quantitative data. Since number of children is a quantitative variable, these 5 numbers are a set of quantitative data. So since these 5 numbers were a set of quantitative data, we we were able to calculate a mean. Since these 5 numbers were a set of quantitative data, we were able to calculate a mean. And since these 5 numbers were a set of quantitative data, we could calculate a mean. Grade level and college major were both qualitative variables. And since they were qualitative variables, this set of data was a set of qualitative data, and this set of data was a set of qualitative data. And you can't calculate the mean of a set of qualitative data because you can't add up the numbers and divide the total by the number of values. So what can we do next? We can find, because you can't add up the values and divide the total by the number of values. We talked about the mean, now let's talk about the median. To find the median of a column of data, you have to put the data values in order from lowest to highest, and then take the middle value. Let's find the median of the data values in the age column. I put the data values in order from lowest to highest, and the middle value is 21. So 21 is the median of this column of data. How could we find the median of the data values in this column? First, we have to put the values in order from lowest to highest. The middle value is 13 because 2 data values are below 13 and 2 data values are above 15. Since 13 is the middle data value, it's the median. One important thing to remember is that you have to put the data values in order from lowest to highest before you find the median. It would be incorrect to just say that the third data value in this column is the median, because these values aren't in order from lowest to highest. Let's find the median of the number of children column. We put the values in order from lowest to highest, and the middle value is 1, so the median is 1. It looks like in this column of data, the mean and the median came out to the same number, and in this column of data, the mean and the median came out to the same number. That can happen sometimes. I'm sorry, I made a mistake. The median of this column of data was 1. That's why I said the mean and the median came out to the same number. And it's fine that the mean and the median came out to the same number because that can happen sometimes. Let's think about whether we can find the median of the grade levels. Grade level is an ordinal variable, so these 5 data values in here or a set of ordinal data. You actually can find the median of a set of ordinal data as long as you have an odd number of data values. Let's put these let's put these 5 grade levels in order from lowest to highest. The median is sophomore because that's the middle data value when the data values are in order from lowest to highest. Right now I'm writing that the median equals sophomore. Up here I'll say that there was no mean. Can we find the median of the college majors? College major is a nominal variable. So these 5 data values are a set of nominal data. You actually can't find the median of a set of nominal data because there's no way to put the data values in order from lowest to highest. If we can't arrange the data values in order from lowest to highest, like we did here, then we can't find the median. So these data values have no mean and no median. When you have a set of quantitative data, you can find the mean and the median. When you have a set of ordinal data, you can find a median, but you can't find a mean. And when you have a set of nominal data, you can't find a mean or a median. I'm writing ordinal up here, but remember that ordinal is a type of qualitative. And remember that nominal is a type of qualitative. When you have qualitative data, you can never calculate a mean, but you can find a median as long as the data is ordinal. You can't find a median if the data is nominal. How could we find the median if we had an even number of numbers? What if we had 18, 30, 21, and 40? What if we only collect data from 4 people? We would still put the values in order from lowest to highest. Notice that when we have 4 values, we have 2 middle numbers. Whenever you have an even number of numbers, you have 2 middle values. How can we find the median if we have 2 middle values? What you do is you add the 2 middle values and divide the total by 2. You find the mean of the 2 middle values. And then the mean of the 2 middle values is the median. The median of these 4 numbers down here is 25.5. If you have a set of quantitative data, you can find the median with an even number of numbers or with an odd number of numbers. If you have an odd number of numbers, you just take the middle value. And if you have an even number of numbers, you find the mean of the 2 middle values. What if you have a set of ordinal data and you have an even number of values? In that case, you can't find the median. If I had freshman, sophomore, freshman, senior, with no junior, this would be my set of data. It would be freshman, freshman, sophomore, junior. I have 2 middle values, which are freshman and sophomore. I can't add the 2 middle values and divide the total by 2. So if I have an even number of ordinal values, there's no clear way to find a median. I can only find the median if I have an odd number of ordinal values. Let's now talk about the mode. The mode is just the value that appears the largest number of times. If we look in the age column, we'll notice that 21 shows up 2 times, and all of the other numbers only show up 1 time. So the mode is 21. The mode and the median are actually the same in this column. In this column of data, 13 shows up 2 times, and 12 also shows up 2 times. So 13 and 12 are both tied for first place, which means we actually have 2 modes. The modes are 12 and 13. In this column, the mode is 2. No, wait. 2 shows up 2 times, and 0 shows up 2 times. So we have 2 modes. The modes are 2 and 0. In this column of data, freshman shows up twice, and all of the other grade levels only show up once. So the mode is freshman. In this column of data, psychology shows up twice, and all of the other majors only show up once. So the mode is psychology. we were able to find the mode of all 5 columns of data. You can find a mode with any type of data. You can find the mode of a set of quantitative data, you can find the mode of a set of ordinal data, you can find the mode of a set of nominal data. So when you have a set of quantitative data, you can find the mean, median, and mode. When you have a set of ordinal data, you can't find the mean, but you can find the median as long as there's an odd number of values, and you can find the mode. When you have a set of nominal data, you can't find the mean or the median, but you can find the mode. Sometimes a set of data will have no mode. What if the ages were 18, 30, 21, 40, and 22? Now each value only shows up one time. No number repeats itself. In this case, there's no mode, because no number shows up more than any other number. We covered the 3 measures of central tendency, which are the mean, median, and mode. Now we'll cover the 4 measures of dispersion. Before we cover them, I wanted to talk about the idea of dispersion, or the idea of spread. Spread and dispersion pretty much mean the same thing. The idea of dispersion is the idea of how spread out different things are from each other. So think about the houses in somewhere like San Francisco, where the houses are all very close to each other. They're so close to each other, they look like they're almost touching each other. This would be an example of low dispersion or low spread between houses. The houses are not very spread out. They're very close to each other. So the dispersion is low, or in other words, the spread is low. I said this could be somewhere like San Francisco. If you go to a rural area where people own more property, you'll see that the houses are further apart from each other. Because in areas where people might have farmland, the houses would be farther apart from each other because people would be owning more property. So in this type of area, the houses would have more spread. I mean, there would be more spread between the houses. So you could say that this is high dispersion between houses. I said that dispersion and spread pretty much mean the same thing, so I could have written low dispersion / spread between houses right here. I could have written high dispersion / spread between houses here. But now what about cars driving on a freeway? Let's think about the speeds of different cars driving on a freeway. If the speeds of all the different cars are similar to each other, then that's low spread. I mean, that would be an example of low dispersion between the different speeds of the different cars on the freeway. So if there were 10 cars driving on a freeway at the same time, and their speeds were 65, 62, 61, 63, 65, 62, 64, and so on, that would be an example of low spread between the speeds of the different cars. I can even draw an example. Let's imagine that these are 10 cars driving on a freeway, and they're all driving. We could say that they're all driving on the freeway at the same time. And I'll write the speeds of the cars. I'll write the speed above each car. This car is driving at 65 miles an hour. This car is driving 63. Maybe this car is driving 66. I'll just write the speed that each car is driving. I'm just making up these numbers as an example to show a low amount of spread or a low amount of dispersion. Notice how these speeds are all very close to each other. We have some cars going 64, some going 63, but the speeds are all pretty much between 64 and 66 miles per hour, or between 63 and 66 miles per hour. So these cars are all driving at very similar speeds. So there isn't very much dispersion between the different speeds that these cars are driving. You can even see the dispersion if we made a little graph like this. Maybe I'll put each car above its own place on this number line. Maybe I'll just make an X for each car. So let's see, we have one car going 63. So 63 is about right here. How many cars are going 64? We actually have 2 cars going 63. So there would be 2 cars going 63. So I stack these above each other just to show that these 2 cars, which I wrote out as X's, are both going 63. So they're stacked right above each other. We have 1, 2, 64s. Maybe, I guess 64 would be about here. There's 2 more X's. And then, how many 65s? 1, 2, 3. Those would all be right here. And then 166 would be out here. This X right here is supposed to be the car that's going 66 miles per hour. Notice how these speeds are all very close to each other. They're all clustered very close to each other on this number line. That's why this would be an example of low dispersion between the speeds of cars. Now let's look at another example. Maybe I'll put it over here. What if instead of these speeds, what if we had one car going 80 and another car going maybe 55. And maybe we have some other cars going at some other speeds. Maybe one car is even going 90 miles per hour. And one car is going very slowly at 40 miles per hour, which would be slow for driving on a freeway. You now have an example of 10 cars that have a higher amount of dispersion between their speeds. The speeds are now further apart from each other, so this would be a higher amount of dispersion between the speeds of the cars. And we can even see that if we made a number line. Now we have one car going 65 miles per hour. That car will be right here. We have one car going 80. We have one car going 90, so we have to extend the number line out even further. So we have 65, 80, well, I mean, 65, 80, 90, 66 would be right here. We have two 65s. 40 would be way out here. So the fact that we have to extend the number line shows that our spread is going up. We have 140 right here. We have another 66 and a 55. 63 would be about right here. And then 64 would be about right here. So notice how these speeds are spread out far apart from each other on this number line. They're spread out across this wide distance. So this is a high amount of dispersion between the speeds of the cars, unlike over here where we had a low amount of dispersion between the speeds because the speeds of the cars were all very similar and close to each other right here. Now, I wanted to give you another way of visualizing the amount of dispersion between us in a set of numbers. What I wanted to do was start off with a list of numbers with very low dispersion and then talk about how we could change the numbers to make the dispersion go up. These numbers have low dispersion because the numbers are all close to each other. They're all one apart. So if we took, well, first let's talk about how the gaps between each of these numbers is a gap of 1 because these two numbers are 1 apart, these two numbers are 1 apart, and all of the numbers are 1 apart. this is a gap of 1, this is a gap of 1, and this is a gap of 1, or a distance of 1. If we take one of these gaps and make it bigger, our spread will go up. So let's take this gap of 1 right here and make it a gap of 2. How can we do that? Well, if we want these numbers to be 2 apart instead of 1 apart, instead of going from 11 to 12, we'll have to go from 11 to 13. And then let's leave this as a gap of 1. So it'll go from 13 to 14. Maybe we'll leave this as a gap of 1, so it'll go from 14 to 15. Now what if we wanted to make the dispersion even higher? Well, if we take this gap and make this gap even wider, that would increase the dispersion. So if we change this to a gap of 4 or a gap of 5, the dispersion would go up. And if we took one of these other gaps and made it bigger, that would also raise the dispersion. For example, if we took this gap here and made it a gap of, let's say, 3 instead of 1, that would raise the dispersion. Let's try that. So these two numbers will still be 1 apart. We're saying that these two numbers will still be 2 apart. But now, these two numbers will now be 3 apart, so now it'll go from 13 to 16. And let's say that these last two numbers are still 1 apart, so it'll go from 16 to 17. So now we have a set of numbers with the lowest amount of spread, the lowest amount of dispersion. We have a set of numbers with a medium amount of dispersion, and we have a set of numbers with the highest amount of dispersion. So as we go from this list to this list to this list, the dispersion is going up. This list has more dispersion than this list, and this list has more dispersion than this list. Now, if we wanted to measure the dispersion, we would want to calculate some value that could actually show that this set of numbers has the lowest dispersion, and this set of numbers has the highest dispersion, and that this list has a dispersion in between, or you could say a medium amount of dispersion, I guess. And we'll talk about how we can actually calculate a value that can do that. But first, let's talk about a little bit more about why is it important to measure the amount of dispersion in a set of numbers, or in a set of quantitative data. Well, the reason why we want to measure spread is because if all we do is calculate a measure of central tendency, such as the mean, that doesn't tell us everything about the data. Let's imagine that I'm working at a job, and I'm working at a school, and my job is to record the final exam scores of a class of 20 students, and then report what I find about their exam scores to the principal of the school. And let's say I record their 20 final exam scores, and I find out that the mean of the class is 75%. So I found out that if I added their 20 final exam scores, and I divided the total by 20, and I got an average of 75, or a mean of 75. And then I go to the principal and I say, I found out that the mean was 75. The mean final exam score was 75. Well, the principal probably isn't going to be satisfied with just knowing the mean, because
there's different possibilities that could be true. I mean, one possibility, or one extreme possibility, is that half the class earned 50s and the other half earned 100s. So if half the class got 50s and the other half got 100s, that would give you a mean of 75. And that would be an extreme high amount of spread, because half the class is way down here and half the class is way up here. The other extreme would be if the entire class got all 75. So if every student got 75%, that would also give me an average of, or a mean of 75. That would be a very low amount of spread. It would actually be no spread at all. If every student earned 75, meaning every student had the same final exam score, that would be no spread. So I said we have one extreme down here with all students earning 75%, which is no spread, and an extreme over here with half the students earning 50s and half of them earning 100s, which would be, that would actually be the maximum or the highest amount of spread possible. Now, realistically, the amount of spread between the students' final exam scores will be somewhere in between those two extremes, but the principal will still be interested in knowing where between those two extremes the class is. Is the class closer to the high amount of spread over here, or is it closer to the lower end of spread down here? In order for the principal to know where or how much spread there is between the students' final exam scores, I would have to calculate a measure of dispersion and give the measure of dispersion to the principal along with the mean. Now let's talk about how to calculate measures of dispersion with a set of data. Let's say that there's a family of 5 people, and a certain person recorded the heights of all 5 family members, and the person ended up with this data set right here. This person collected data from an entire population, because a family of 5 people is a complete population, because a family of 5 people is a complete group of people that have something in common with each other. So if the person recorded data from all 5 family members, then the person did collect data from an entire population. The person collected data from an entire population because the person didn't leave out any family members. Let's say that another person recorded data from 3 out of the 5 family members. This person recorded the heights of 3 out of the 5 family members, and that person ended up with this data set right here. So this person recorded the heights of person 1, person 3, and person 4, but not persons 2 and 5. Since this person didn't collect data from all 5 family members, this person didn't collect data from the entire population. This person collected data from a sample of 3 out of the 5 population members. Let's say that the person who recorded data from the entire population of all 5 family members wants to measure the amount of dispersion in his or her data set right here. And the person who recorded the heights of a sample of 3 out of the 5 family members also wants to measure the amount of dispersion in his or her data set right here. How could these people measure the amount of spread in their data sets? The simplest way to measure the amount of dispersion in a set of data is with something called the range. To get the range, you just subtract the highest value by the lowest value. So I'll write that right here. Or you could say it's the maximum value minus the minimum value. Now let's calculate the range for the population of all 5 family members. The tallest person in the family is 84 inches tall, and the shortest person is 56 inches tall. So the highest value is 84, and the lowest value is 56. If we subtract 84 by 56, we get 28. So the range of the entire population is 28. Let's calculate the range for the sample. The highest value in the sample is 65, and the lowest value in the sample is 56. So if we subtract 65 by 56, we get 8. Oh no, wait, 9. So it's looking like the sample is less spread out than the population, meaning it looks like the numbers in the sample are closer together and have less dispersion, and it looks like the numbers in the entire population are more spread out and have more dispersion. The reason why the population has more dispersion is because the population includes 84, which is a pretty extreme value that's far away from the other values. And since the sample doesn't include 84, and it doesn't include that extreme value, it has less dispersion. So since the sample has less dispersion than the population, it ended up with a lower range. Now what's another way we could calculate the amount of spread, or the amount of dispersion? There's actually another way to calculate the amount of spread, or the amount of dispersion that's better than the range. And first I'll talk about the problem with the range. Let's compare the ranges of these 3 sets of numbers. These sets of numbers might look a little bit strange, but I'm just using these numbers to make a point. Let's think about which set of numbers has the lowest dispersion and which set of numbers has the highest dispersion. Well, these 3 numbers are close together. They're only 1 apart. These 3 numbers are 2 apart, so these 3 numbers have more dispersion than these 3 numbers over here. And these 3 numbers are 3 apart, which is more dispersion. So as we go from this list to this list to this list, we're seeing more and more dispersion between these 3 middle numbers. Right here, the 3 middle numbers are 1 apart. Here they're 2 apart, and here they're 3 apart. And in all 3 sets of numbers, the other 2 numbers are 10 and 20. So the other 2 numbers don't change. So actually, because of the middle 3 numbers, this list has the lowest dispersion, this list has the highest dispersion, and this list is in between. Now, if the amount of dispersion is going up as we go from left to right, you might think that the range should go up from left to right. And let's see what happens. The range is just the highest value minus the lowest value. So The highest is 20, the lowest is 10. If we subtract 20 by 10, we get 10. Here the highest is 20 and the lowest is 10. And if we subtract 20 by 10, we get 10. And here if we subtract 20 by 10, we get 10. The highest is 20, the lowest is 10. When we subtract the highest by the lowest, we get 10. So even though the overall amount of dispersion is going up as we go from left to right, the range isn't changing. Even though these lists of numbers have different amounts of dispersion, they all have the same range. And that's a problem with the range. Sometimes even though the amount of dispersion is going up, the range won't change. It'll just stay the same. So in other words, it's possible for different sets of numbers that have different amounts of spread to all have the same range. And that's a problem with the range because we can see that even though these lists have different amounts of dispersion, the range isn't showing that that's true. So we need a better measure of dispersion. Basically the problem with the range is it's only affected by the highest and lowest values. It doesn't say anything about the values in between, the lowest and highest values. So since it only shows the distance between the highest and lowest values, and it doesn't show the amount of dispersion between the middle values, that's a problem with the range. Now we'll talk about other measures of dispersion that don't have that problem. Let's talk about another measure of dispersion that doesn't just show the distance between the highest and lowest values. Let's talk about a measure of dispersion that actually does measure the overall amount of spread between all of the numbers in the data set. One measure of dispersion that does measure the overall spread between all of the numbers is called the mean absolute deviation. And right now I'll list the steps to get the mean absolute deviation. First we have to find the mean of the data set. Next we have to subtract each data value by the mean. To get values called deviations. Next we have to find the absolute value of each deviation. And then find the mean of the deviations. And I'll explain what the word deviation means when I go through these steps. So first we have to find the mean of the data set. Let's do it with the population first, and then with the sample. So what's the mean of this population? To get the mean, we have to add the 5 numbers and divide the total by 5. What do we get when we add these 5 numbers? Well, the total comes out to 330. And we have to divide by 5 since we have 5 numbers. And we get 66. So the mean of the entire population is 66. Right here I'll write data, so we remember that this is the set of data. Right now we're going to subtract each number, or each data value, by the mean of 66. Maybe I'll move this down a little bit. So the reason I wrote the word mean right there is to show that each number that I'm writing in this column is just the mean of 66. Let's subtract all of these. 60 minus 66 is negative 6. 84 minus 66 is 18. 65 minus 66 is negative 1. 56 minus 66 is negative 10. And 65 minus 66 is negative 1. Let me double check these. This is correct. This one's correct. Looks like they're all correct. These values here are called deviations. They're just the answers that we get after we subtract each value by the mean. So I'll write deviations right here. I'll erase this. This is just the work we did to get the mean of 66. So now we've already finished the first 2 steps. We found the mean of the data set and we subtracted each value by the mean to get the deviations. Next we have to find the absolute value of each deviation. We have to get the absolute value of each of these numbers. To get the absolute value of a number, you just take the number and leave off the sign. So if it's a positive number, it just stays the way it is. It stays positive. And if it's a negative number, it just changes to a positive number. Let's find the absolute value of each of these deviations. So we'll call them absolute deviations. The absolute value of negative 6 is 6 because to get the absolute value of a negative number, you just take the number and leave off the negative sign. This value is 18, which is a positive number, If it's a positive number, it just stays the way it is. So it'll just stay 18. Negative 1 becomes 1 when we leave off the negative sign. Negative 10 becomes 10. And negative 1 becomes 1. And if we had a 0 in here, then 0 would just stay 0 because the absolute value of 0 is 0. So now we finished step 3. We found the absolute value of each deviation. Now we can do the last step, which is finding the mean of the deviations. Sorry, this should be different. It's actually finding the mean of the absolute deviations. So let's do that. To get the mean of the absolute deviations, we just add these 5 numbers and divide the total by 5. We're pretty much just finding the mean of this list of numbers right here. We add them and we divide by 5, because we're dividing by the number of numbers. There's 5 numbers in here, so we divide by 5. Let's add the numbers on top. 6 plus 18 is 24. 24 plus 1 is 25. 25 plus 10 is 35. And 35 plus 1 is 36. So 25, 24, 25, 35, 36. Now we just need to find, we added the numbers, and we got a total of 36. Now we divide by 5. We get 7.2. So the mean absolute deviation of the entire population is 7.2. I'll abbreviate like this. Now let's find the mean absolute deviation of the sample. We have to follow these same steps. First, we have to find the mean of the sample. Since the sample includes 3 numbers, we add the 3 numbers and divide the total by 3. Let's add these 3 numbers. The total is 181. So we'll divide 181 by 3, and we get 60.33. finished step 1 and found the mean of the data set. Step 2 is subtracting each data value by the mean. In order to make this easier so that we don't have to deal with decimals, let's round this mean from 60.33 down to 60. Let's round it to the nearest whole number. So we're going to be subtracting each of these by 60, since we rounded the mean to 60. We're doing step 2, which is subtracting each value by the mean. $60 minus 60 is 0. 65 minus 60 is 5. And 56 minus 60 is negative 4. These are our deviations. I'll just write DEV. That finishes step 2. Now we need to do step 3, which is finding the absolute value of each deviation. I'll write ABS DEV for absolute deviation. The absolute value of 0 is just 0. The absolute value of 5 is 5, because if it's a positive number, it just stays the way it is. And the absolute value of negative 4 is 4. We just leave off the negative sign. So we found the absolute deviations, which was step 3. In step 4, we have to find the mean of the absolute deviations. That just means we have to find the mean of these 3 numbers. To get the mean of these 3 numbers, we just add the 3 numbers and divide the total by 3. We're just adding and dividing by the number of numbers. The top equals 9. We divide by 3. So we added the 3 numbers and we got a total of 9. Now we're dividing by 3 and we get 3. So the mean absolute deviation of the sample is 3. Remember how I said that the sample has less dispersion and the population has more dispersion? Since the population has more dispersion than the sample, that's why the population has a higher mean absolute deviation than the sample. We have a list of numbers right here, and we have a list of numbers right here. The list of numbers that has the most dispersion will have the higher mean absolute deviation, and the list of numbers that has lower dispersion will have the lower mean absolute deviation, because as the dispersion goes up, the mean absolute deviation goes up along with it. So the reason why the population has the higher mean absolute deviation is because the population has more dispersion than the sample. Now you might be wondering why we didn't just find the mean of this column of numbers. Why didn't we just find the mean of the deviations? The problem is, if you try to add the deviations, they'll add up to 0. And that'll actually always happen. no matter what list of numbers you're dealing with, the deviations always add up to 0 because the negative numbers and the positive numbers cancel out. So if you tried to add up these numbers on your own, you would see that they add up to 0. And if you tried to add up, let's see, these numbers should also add up to 0. The reason that they don't is because we rounded the mean before we did the formula. We didn't use the exact mean. But if we did use the exact mean of 60.33, then these would add up to 0. Since the deviations add up to 0, that gets you to a dead end, because once you get to 0, it's not clear what step should be done next. So the formula ends up at a dead end, and you don't want that to happen, so what you do is you find the absolute values of the deviations, which makes all the numbers positive, and then the numbers don't add up to 0. And you can actually, which means since these numbers don't add up to 0, you can find the mean of these numbers, even though you can't find the mean of these numbers over here, since they add up to 0. And if we tried to find the mean of these numbers, they would add up to 0, and then 0 divided by 5 is just 0. Now, I said that the reason that we found absolute values is to make all of the numbers positive so that they wouldn't add up to 0. There's actually another way to make the numbers positive besides finding the absolute values, and that's what I'll show you next. I'm going to show you how to calculate two other measures of dispersion called the variance and standard deviation. And to find the variance and standard deviation, you have to actually find squared deviations. And before I show you how to find squared deviations, I'll write out the steps for the variance and standard deviation. Step 1, well actually step 1 and 2 are the same, so I'll just copy and paste them. Oh, I meant to copy and paste steps 1 and 2. And in order for it to fit, I have to get rid of these numbers over here. Step 3 is squaring each deviation, instead of finding the absolute value of each deviation. And then step 4 is finding the mean of the squared deviations. And it's actually You actually use an adjusted formula if the data comes from a sample. I'll show you what I mean when we go through the steps. And then step 5 is finding the square root of your answer from step 4. If you stop at step 4 and don't go to step 5, your value is called a variance. If you do go on to step 5, then the answer you get from step 5 is a standard deviation. Let's find the variance and standard deviation of the entire population. Step 1 is finding the mean of the data set. We already have the mean of the population. We found out that the mean was 66. So we've already finished step 1. We've also already finished step 2 because we already have deviations. We already subtracted each number by the mean. We can move on to step 3, which is squaring each deviation. We need to make a new column of squared deviations. We're going to square each of these deviations. What that means is we're just going to multiply each deviation by itself. So first we're going to multiply negative 6 by negative 6. When you multiply a negative number by a negative number, you get a positive answer. So negative 6 times negative 6 is just 36. You get the same answer that you would have had if you had multiplied 6 times 6. Let's now do it with 18. 18 squared is 18 times 18. So just multiplying each deviation by itself. We get 324. Next we'll just multiply negative 1 by itself, which will be negative 1 times negative 1. Negative 1 times negative 1 is just 1. The negatives cancel out. Negative 10 times negative 10. That's the same. That gives you the same answer as 10 times 10. The two negatives cancel out, and you get, well, 10 times 10 is 100. Now we have negative 1 times negative 1 again. Which is just 1. So now we have all of our squared deviations. We'll put them in here. So now we finished step 3, we've squared each deviation. The next step is finding the mean of the squared deviations. I mentioned an adjustment here. We actually don't do any adjustment if the data comes from an entire population, like it does here. We just find the mean of the squared deviations. So how do we do that? Well, the mean of the squared deviations will just be the total of the squared deviations divided by 5. It's just the mean of these 5 numbers. So let's add those 5 numbers and divide by 5. Let's add the 5 numbers and then divide. We're going to add the squared deviations and then divide the total by 5, since we have 5 squared deviations in here. So the total is 462. Now we divide 462 by 5, and we get our answer. We get 92.4. So the variance is just the mean of the squared deviations. Just like how the mean absolute deviation was the mean of the absolute deviations, the variance is just the mean of the squared deviations. It came out to 92.4. Sometimes I like to write out the work like this. For the mean absolute deviation and the standard deviation. For the mean absolute deviation and the variance. And what we just added and divided by 5. Oh, it was 92.4. That was the variance. So to get the variance, we added the squared deviations and divided the total by 5. Because I said if you stop at step 4, you get the variance. If you stop at the mean of the squared deviations, you get the variance. If you go one step further and find the square root of the variance, you get a number called the standard deviation. So this was our variance. If we find the square root of the variance, we get the standard deviation. To get the square root, we can just press the square root key right here, and it comes out to about 9.61. So this is the standard deviation. I can just write STDEV, and remember that this right here was the mean absolute deviation. I'll just write it like this. Now let's try to find the variance and standard deviation of the sample. We've already done steps 1 and 2 because we already have our deviations. We can skip to step 3, which is squaring each deviation. So we need our column of squared deviations. So we'll start with 0, which is the first deviation, and square it. 0 times 0 is just 0, meaning 0 squared is 0. 5 squared, which is 5 times 5, is 25. And negative 4 squared, which is negative 4 times negative 4, is 16, because the negatives cancel out. So we finished step 3, we squared all the deviations. Now we have to do step 4. Remember when we found the variance of the population, we just found the mean of the squared deviations in step 4. But notice how it says if it's a sample, you find an adjusted mean. And the way it's adjusted is actually, instead of dividing by the number of numbers, which would be 3, you divide by 1 less than the number of numbers. That's what makes it an adjusted average, or an adjusted mean. So let's add the squared deviations. They add up to 41. We divide by 1 less than the number of numbers, which means we divide by 2, because 2 is 1 less than 3. There's actually a notation for this. It's actually called n minus 1, because n is the number of numbers, so n is 3, and what we're dividing by is 1 less than n. So we're dividing by n minus 1. And we only divide by n minus 1 if the data came from a sample. If the data came from a population, you just divide by the number of numbers. you just divide by n. 41 divided by 2 is 20.5. That's the variance of our sample. And if you want the standard deviation, you just move on to step 5, which is just finding the square root of the variance. What's the square root of 20.5? We can hit the square root key, and it's about 4.53. So this is our standard deviation. Remember how I said that the mean absolute deviation was higher over here? I mean, the mean absolute deviation was 3 here, and it was 7.2 over here. And the reason why it came out to a higher number with the entire population is because the population had more dispersion. The idea is that with any measure of dispersion, the value should come out to a higher number when the data set has more dispersion, which means that since the variance and standard deviation are also measuring the dispersion, the variance and standard deviation of the population should come out higher, and the variance and standard deviation of the sample should come out lower, because the population has more dispersion and the sample has less dispersion. And let's check to see if that happened. The variance of the population is 92.4, and the variance of the sample is 20.5. So the variance of the population did come out higher because it has more dispersion, and the standard deviation of the population was 9.61, and the standard deviation of the sample was 4.53. So the standard deviation of the population did come out higher than the standard deviation of the sample. The reason why is because the population has more dispersion and the sample has less dispersion. So we can see that anytime you calculate a value to measure the dispersion, the value will come out higher when the data set has more dispersion. Or at least that's true with all of the good measures of dispersion. The exception was the range. We could see that the range doesn't always come out to a higher number when the data has more spread, but the other three, the mean absolute deviation, variance, and standard deviation, will come out higher when the data has more spread. It'll always come out higher when the data has more spread. Now, since the variance and standard deviation over here used a slightly different formula than the variance and standard deviation over here, there's actually different terms or different words that are used. When you have a data from an entire population and you calculate the variance without using the adjustment in step 4, your answer is actually called a population variance. I can just write POP for population, and if you find the square root of that variance, then your answer is called a population standard deviation. And if you have data from a sample and you do use this adjustment in step 4, your answer right here would be called a population variance. I'm sorry, a sample variance. And when you find the square root of the sample variance, your answer is called a sample standard deviation. So it's just a more specific way of describing these values. So one reason why they use different words is because these values right here are calculated with a population, and these values are calculated with a sample. And another reason is because these values right here are calculated with a slightly different formula than these values over here. Now let's talk about why there's this adjustment when you have data from a sample. When you calculate the variance or standard deviation to measure the spread of a sample, the goal is to get a rough idea or to estimate the spread of the entire population. In other words, the purpose of calculating the sample variance or sample standard deviation is to try to get a rough idea of what the population variance or population standard deviation equals. So the sample variance right here is meant to estimate the population variance over here, and the sample standard deviation here is meant to estimate the population standard deviation over here. A sample value estimates the population value, and we see right here that the sample values came out smaller than the population values, and the reason why is because the sample had less dispersion than the entire population. And when you take a sample from the population, this actually tends to happen often. There's actually a tendency for samples to have less spread than the populations they come from. The reason why is because samples don't capture all of the extreme values that are found in the entire population. Just like how this sample didn't capture the extreme value of 84. So what this means is that if you don't use any adjustment, your sample variance and sample standard deviation will tend to underestimate the population variance and standard deviation because of the sample having less spread than the population. And what this adjustment is meant to do is to bring up the sample variance and standard deviation to a higher number. It's meant to boost them up higher so that they're closer to what the variance and standard deviation equal for the entire population. So if we didn't do this adjustment and we calculated the variance and standard deviation the same way as we did over here, these values would come out even smaller, which would mean that they would be even further below the population values. So when you divide by one less, you're dividing by a smaller number. And when you divide by a smaller number, you get a bigger answer. And when this comes out to a bigger answer, then this also comes out to a bigger answer, which means that these two values are, by using this adjustment, these two values were brought up closer to what the population values equal. So they're not these two values right here aren't underestimating these values as much as they would be if we didn't use that adjustment. And the reason why there's no adjustment for the mean absolute deviation or the range is because no adjustment has been developed because these values are pretty much never used to measure spread. really only the variance and standard deviation are used in actual research. Actually, if you're reading journal articles about the results of psychological studies, the only value out of these 4 values that you'll usually see is the standard deviation. You'll usually see the mean and the standard deviation together. So the standard deviation is what's almost always used to measure spread in psychological studies. I wanted to talk a little bit more about the advantages and disadvantages of these different measures of dispersion. We know that the range has the disadvantage of only measuring the distance between the highest and lowest values. And the variance also has a disadvantage. The disadvantage of the variance is the squaring makes it come out to a fairly high number. And since it comes out to such a high number, it's difficult to understand what it's really showing about the data. And the mean absolute deviation and the standard deviation don't have that advantage, don't have that disadvantage, because they don't come out to such a large number. The advantage of the mean absolute deviation and the standard deviation is that they give you an idea of how far the data values are from the mean. Let's talk about what I mean by that. Each of the absolute deviations is just the distance between a certain data value and the mean. This row has an absolute deviation of 6, and what this absolute deviation of 6 is showing is that this data value of 60, this person's data value of 60, is 6 away from the mean of 66. What this absolute deviation of 18 is showing is that this person's data value of 84 is 18 away from the mean of 66. And this person's data value of 65 is showing that this person's data value is 1 away from the mean of 66. So each of the absolute deviations is just the distance from a certain data value and the mean. And if you calculate the average or the mean of the absolute deviations to get the mean absolute deviation, what you found is just the mean of all of the distances. So it's really just the mean or the average distance from each data value to the mean. What this mean absolute deviation of 7.2 is saying is that the average distance between each data value and the mean of 66 is 7.2. So the mean absolute deviation literally is the average distance from each data value to the mean. And notice how the standard deviation comes out to a number close to the mean absolute deviation. If we look at the population of 5 people, the mean absolute deviation is 7.2, and the standard deviation is 9.61. So since they come out close to each other, you could say that the mean absolute deviation is the average distance from each data value to the mean, and the standard deviation is a number that's roughly showing the average distance from each data value to the mean. The same thing with a sample. The mean absolute deviation right here is the literal average distance from each number to the mean, because if you take these numbers right here, the absolute deviations, and you average them to get the average of 3, you get the average distance from each data value to the mean. And then if you calculate the standard deviation, you get a number close to the mean absolute deviation. So once again, the mean absolute deviation is the average distance from each data value to the mean, and the standard deviation is a number that roughly shows the average distance from each data value to the mean. So you could say that the mean absolute deviation and the standard deviation both have the advantage of showing the average distance from each data value to the mean. So the disadvantage of the range is that it only shows the distance between the highest and lowest values. The disadvantage of the variance is that it comes out to such a large number, and it's difficult to understand what it's really showing about the data. And the advantage of the mean absolute deviation and standard deviation are that it gives you a sense of how far the numbers are from the mean on average. Let's now talk about the terms population parameter and sample statistic. A population parameter is a value that describes an entire population. And a sample statistic is a value that describes a sample. Let's look at some examples. Before I do this, actually, let's look back at the last slide. Remember how all of these values here on this left side of the board were calculated with an entire population? Since they were all calculated with an entire population, they would all be called population parameters. So this range right here, this variance, this standard deviation, and this mean absolute deviation would all be called population parameters. These same values over here, the range of the sample, the mean absolute deviation of the sample, and the variance and standard deviation of the sample would all be called sample statistics because they were all calculated with a sample. So let's go back over here. One example of a population parameter is a population mean, which is the mean of an entire population. What could be an example? Maybe the mean GPA of all 20,642,819 college students in the US. If you were able to record the GPAs of all 20,642,819 college students in the US, add those GPAs, and then divide the total by this number right here, your answer would be the population mean. And it would also be called a population parameter because it's a value that is calculated with an entire population. Another example is a population median would also be a population parameter. A population variance, meaning a variance that's calculated with an entire population. A population standard deviation. So if you recorded the GPAs of all of these college students, meaning you recorded the GPAs of every college student in the US, and then you used the answers to calculate a variance and a standard deviation, your answers will be called a population variance and a population standard deviation. and both of them would be called population parameters, just like how the population mean would be a population parameter. What about sample statistics? All of these values here are called sample statistics if they're calculated with data from a sample and not from an entire population. So a sample mean would be a sample statistic. And an example of a sample mean could be the mean GPA of 200 selected college students living in the US. So if I selected 200 college students, I recorded their GPAs, I added those 200 GPAs and divided the total by 200, I would get a sample mean, and that sample mean would be called a sample statistic. Also, if I found the median of the 200 GPAs, my answer would be called a sample median, and that would also be a sample statistic. If I calculated the variance of the 200 GPAs, I would have a sample variance. And if I calculated the standard deviation of 200 numbers, I would have a sample standard deviation, and that would also be a sample statistic. And there's actually symbols that are used for these different values. All of the population parameters have a Greek symbol. The symbol for a population mean is the Greek letter mu, which looks like a U, and it's pronounced this way. We don't talk about median. The symbol for a variance is sigma squared. That Greek letter is called a sigma. And a population standard deviation is just sigma. For sample statistics, they don't use Greek letters. The symbol for a sample mean is x. It's called x bar. It's an x with a bar above it. Sample variance is the letter s squared, and it's just called s squared. And then sample standard deviation is just s. The reason why this is just sigma is because it's the square root of the variance, and the reason why this is just s is because it's the square root of the variance. I won't go over the symbols for median. I wanted to also go over the symbols for sample size and population size. Those don't really fall into these categories, so I'll put them over here. Population size is a capital letter N, and sample size is a lowercase n. And if we wanted to go back to this slide right here, we could use some of those symbols. We said that the mean of the entire population was 66, so it would be mu equals 66. And the mean of the sample came out to 60.33. So over here we could say x bar, the sample mean, equals 60.33. And this was a population standard deviation. So we could say sigma equals 9.61. This standard deviation over here was a sample standard deviation, so we could use the letter S. We could say S equals 4.53. And one of the most important things as we go on is to remember that a population mean isn't the same thing as a sample mean. And also that a population standard deviation isn't the same thing as a sample standard deviation. If you can remember those things, that'll make a lot of the later topics a lot easier. And since we don't collect data from entire populations, since they're too large to collect data from, we hardly ever actually calculate population parameters. For example, no one would actually calculate the mean GPA of the entire college student population in the US. What we actually do is we collect data from samples and we calculate sample statistics. And then the sample statistic helps us get a rough idea of what the population parameter equals. For example, a person who's calculating this sample statistic right here is doing that to estimate what this population parameter over here equals. So the sample statistic estimates the population parameter, and that's just because, like we said, the purpose of collecting data from a sample is to learn about the entire population. And the sample statistic won't be exactly equal to the population parameter, but hopefully it'll be close enough to at least give us a rough idea of what it equals. Let's go back to this spreadsheet for a second. I want to talk about how we can use the descriptive statistics that we've been talking about to summarize this set of data. Each column of data is going to have its own descriptive statistics. I'll show you what I mean. The age column will have its mean, its median, its mode, its range, mean absolute deviation, variance, and standard deviation. So we could use this column of data right here, the age column, to calculate all of these values. And we'll get a certain mean, a certain median, a certain mode. We'll get one number for each of these. The number of units column will have its own mean, median, mode, range, and so on. So after we're finished calculating the values for the age column, we can move on and calculate all of the same values for the number of units column. And they're not going to necessarily come out to the same number that they did over here. For example, the mean of this column isn't necessarily the same as the mean of this column, and the median of this column isn't necessarily the same as the median of this column. We could then calculate all of the values over again for the number of children column. And all three of these are quantitative. All three of these are quantitative variables, which means that we can actually calculate all 7 of these values. But grade level is an ordinal variable. It's a variable that has categories that follow in order, but it doesn't have numbers that stand for amounts. So we actually can't calculate a mean for the grade level column. We can calculate a median and a mode. And if it's not quantitative, we can't calculate any of these measures of dispersion that we've been covering. So we actually can't calculate these last 4 values. So for this column, we could calculate a median, a mode, and that's all actually, since it's a column of ordinal data, it's not quantitative. And what about this column right here? College major is a nominal variable, which means it's a variable that has categories, and the possible categories don't follow an order from lowest to highest. What that means is we can't have a median. We can't have a median because there's no way to put these values in order from lowest to highest. So we actually have a mode only. You might be able to guess that since the age column has more dispersion than these two columns, the age column would give us larger numbers for the measures of dispersion, and these two columns would give us smaller numbers for the measures of dispersion. I wanted to do a quick demonstration to show why these values are able to measure the spread of the data. Here we have a column of data, and here we have the mean absolute deviation in yellow. That's just the average of the absolute deviations. We have the variance in red, which is the average of the squared deviations. And we have the standard deviation in green, which is the square root of the variance. Let's see what happens if we change 2 of the numbers to increase the spread of the data. The way I'm going to increase the spread of the data is I'm going to change this number to 5, and I'm going to change this number to 20, which will make the numbers a little bit more spread out. What's going to happen is when I change this number to 5, this data value is going to be further away from the mean of 12.5. Instead of it being 10 minus 12.5, it'll be 5 minus 12.5. So since this number will be further from the mean, it'll give us a bigger deviation right here. And also, if I change this to 20, this data value will be further from the mean of 12.5. So instead of it being 15 minus the mean, it'll be 20 minus the mean, which will give us a bigger deviation right here. So let's see that happen right now. Right, so these 2 deviations have increased. They've now gone up to negative 7.5 and 7.5. And since these 2 deviations increased, the absolute deviations here and here increased in the top and bottom rows. And because these 2 absolute deviations increased, the 2 squared deviations, meaning over here and over here, also increased. And then what happens now is that since these 2 absolute deviations have become higher, the average of the absolute deviations has become higher, which gives us a higher mean absolute deviation. And since these 2 squared deviations have gone up, it makes the average of the squared deviations higher, which gives you a higher variance. And if the variance is higher, then the square root of the variance also goes up, and then gives you a bigger standard deviation. If the variance goes up, the standard deviation has to go up along with it, because the standard deviation is just the square root of the variance. So we can see that when we added more spread to the data, these 3 values all increased. These 3 values measure the spread of the data, so as the data gets more spread out, these 3 values increase. And the reason they increase when the data is more spread out is because when the data is more spread out, the deviations, absolute deviations and squared deviations, become larger numbers. And since they become larger numbers, these 3 values go up.